This is the screencast for section 1.2, example 9, symmetry. I know there is a lot going on this page, but symmetry is kind of a difficult concept to work out and figure out, but it's even harder to understand why it occurs. So we're going to look at each of these examples of symmetry graphically, numerically, and algebraically. So symmetry with respect to the y-axis, the most basic example of that would be your plain old simple parabola x squared. The reason it has symmetry with the y-axis is because the parabola has the same thing going on to the right of the y-axis as it does to the left. So if I plug in positive, so that graphically that's what's happening. Numerically what that means is if I plug in positive 1 and negative 1, I get the same exact y value as an output. As you can see in our numerical chart here, if I plug in negative 1 and positive 1, I get the same value, negative 2 and positive 2, negative 3 and positive 3. Algebraically what that means is if I plug in a negative x into the function, I should get out the same exact value, or that will equal, what I get when I plug in positive x to the function. And we'll look at some examples of these in a second. A nickname, by the way, for this is even symmetry. The next type of symmetry we'll look at is symmetry with respect to the x-axis. This one doesn't have a nickname. You can call it Bob if you want to. X-axis symmetry has the same thing going above and below the x-axis. If you notice, these are not functions. They do not pass the vertical line test. We don't use this very often. You won't see it very often, but it does exist, and it's an example of symmetry that you will be tested on. Now, the third type of symmetry is symmetry with respect to the origin. We call this one odd. What odd symmetry means is that if I take any point, let's call it x comma y, that point will be given the opposite y value when I plug in the opposite x value. So negative x, negative y. In other words, I take x comma y's path to the origin and keep going a second distance away from the origin. It is reflected through the origin. Symmetry to the origin numerically means that every x value I plug in, if I plug in the opposite one, I will get out the opposite y value. So when I plug in positive 1, I get positive 1. But when I plug in negative 1, I get negative 1. If I plug in positive 2, I get positive 8. If I plug in negative 2, I get negative 8. Algebraically, what that means is if I plug in any negative x value, I should get out the opposite f of x value, or y value, as if I were to plug in the positive value of x. So let's look at some examples to kind of clarify what that means algebraically. Example 9, part A. I can tell you right off the bat that this has even symmetry. It looks the same on the left and the right of the y-axis. But algebraically, I have to prove this. I have to show that any x value I plug in is going to have the same value whether it's negative or positive, same y value, whether it's negative or positive. So I'm going to take f of x, and instead I'm going to plug in negative x. So instead of x squared, I'm going to make that negative x squared minus 3. Now what that means is that negative x, when that is squared, negative x times negative x is positive x squared. So I can simplify that to a positive x squared. Any negative number squared is positive. So I found out that when I plugged in negative x to the f function, I got x squared minus 3, which so happens that is the same exact function when x is positive. So because f of negative x eventually equals f of positive x, that is an even symmetry function. Part B. To me, that looks like an even function, or it should be an even function, but if I concentrate on the y-axis, it is not the same on the left of the y-axis as it is on the right of the y-axis. So parabolas all have some sort of symmetry, but specifically even symmetry means it has to be the same on the left and the right of the y-axis. Algebraically, to show that this does not have any symmetry, I'm going to take g and I'm going to plug in negative x. So now I have, instead of positive x squared, negative x, in parentheses, squared, minus 2 times negative x minus 2. G of negative x, let's see, that's going to be negative x squared. We already discussed negative x times negative x is positive x squared. Now a negative 2 times a negative x is a plus 2 minus 2. So g of negative x does not equal g of positive x, nor does it equal the opposite of g of x. In other words, x squared stayed the same sign, positive. The 2x changed from negative to positive, and the minus 2 stayed the same. So we had some things stay the same and some things go opposite, which means there is no symmetry here. Now for part C, it looks to me like this is going to be odd symmetry. It looks like if I look to the top right of the origin and the bottom left of the origin, it kind of looks like it's doing the same thing. Same with the top left and the bottom right. But I have to prove that algebraically. I'm going to plug in negative x to the h function. So in the numerator, that's going to be negative x cubed all over 4 minus negative x squared. So in the numerator, a negative cubed is still a negative. So I have a negative x cubed over, this will be 4 minus, now negative x squared is positive x squared. So that whole function is now the opposite of what I started with. There is now a negative sign in there that wasn't there before. So h of negative x turned out to be the opposite of h of x. Therefore, we have odd symmetry. The now try problem, number 49, also asks us to state whether this is an odd, even, or neither symmetry. Support graphically and confirm algebraically. Well, I'm going to confirm algebraically first before we even look at this graphically. I'm going to plug in negative x and see what I get. So let's see, negative x squared plus 2. If I simplify, negative x squared is positive x squared. When I plugged in a negative x, I get out the same exact thing as when I, as the original function. So if I plug in a negative x, I get out the same thing as whether I plugged in a positive x like the original function. So I think this has even symmetry. Let me check that on my calculator. Just off the top of my head, I'm thinking, well, a square root, I can't take the square root of negatives, so there shouldn't be any function on the left side of the y-axis. But at the same time, I'm squaring those negatives first. So they're turning positive, which means I can take a square root of negatives. So let's see for sure. Square root x squared plus 2. I'm going to zoom 4 this one. Zoom 4 is just a little closer of a zoom. And I can see that that is shaping up to be an even function. Go back to zoom 6. Graphically, I can confirm that that is in fact an even function. What I found algebraically does make sense with my